Welcome to the Lionheart Academy. Today we're continuing our trigonometry lesson. This is our lesson 25 today. We are in the part where we're discussing graphs of trig functions. So we have been talking about graphs of trig function for the last three videos, for the last three lessons. Today is the fourth part of this graph of trig function lessons. Now today I would like to share with you, concentrate on the properties of the graph. Okay, so some of the specific things that we need to know about each of the sine, cosine, tangent graph. So we're going to start with domain range. As you can see, I already created a table here for you. So we're going to have the functions on the first column, and then we're going to have the domain range, zeros, periods, vertical asymptotes, the position of the vertical asymptotes, and then whether the function is classified as even or odd function, and the reciprocal function of that particular function. So those are some of the major things that you will need to be familiarized. You need to be familiar, okay, and something that you should familiarize yourself with. Okay, all right. So let's start. Let's go ahead and take a look at the graph of the sine again. All right. So here I'm going to start out with the real number axis, with marking real numbers 0, 1, 2, 3, 4. We can go ahead and change to pi. Divisions in pi so we can see a little bit better, but again I would like you to just to see how sine graphs looks like in the real number axis with real numbers marking. So about 1.57, this is about 1.7, it will reach the peak, that's about half a pi, and this is about 3.14. Sine increases from 0 to 1 between 0 and pi over 2. From pi over 2 to 3 to pi, the sine decreases from 1 to 0. Then sine further decreases from 0 to -1 between pi over 2 and 3 pi over 2, and then from 3 pi over 2 to 2 pi, sine increases from -1 back to 0. As 2 pi is about 6.28, so that's where that point is. So if I go ahead and change this to step, I'm going to do step pi over 2. Okay, now you can see very clearly everything is pi over 2, and the divisions lines up perfectly. So this is equivalent to our first quadrant. From pi over 2 to pi is equivalent to our second quadrant. From pi over 2 to 3 pi over 2 is equivalent to our third quadrant. From 3 pi over 2 to 2 pi is equivalent to our fourth quadrant. And from 0 to 2 pi, sine completes one cycle. It's one cycle, and so the time to complete that cycle is the period. So for our basic sine, our period is from 0 to 2 pi. Now the domain is the valid input of a function. So our function input is the x value, which is the horizontal value, the independent value is our input. The y value is the output, the dependent value. So as you can see, there's no restrictions. I can zoom out a little bit. I know this is not a proof, but I'm just trying to show you that it seems there's no restrictions for the input of sine. So the domain for the sine function would be all real numbers. All real numbers means that you can plug in any real numbers. Now remember, we're talking about real numbers when we're talking about radian values. We're not using degree. Of course you can put in any degrees as well, but when we graph, we have to graph in real numbers, so we have to use radian. That's why it's important to use radian. We seldom graph using usually when we graph, we don't use degree divisions. We don't put 0 degrees, 90 degrees here. I mean, sometimes you see that in some applications, but most of the applications, in real life applications, most of the applications we use radian here. I'm sure there are applications that you can graph using degrees, but we're going to be using radian. That's why it's important to know your radians, and then how to convert. This is about radian. This is pi over 4, and this is about pi over 6. This is about pi over 3. If I can go ahead and further zoom in, you might be able to see that, or I can change this to pi over 6. Then you'll be able to see, yes, okay, so it's pi over 6, pi over 3, pi over 2. So those are the major divisions that we need to familiarize ourselves with. Okay, all right, so definitely the domain of sine is all real numbers. Okay, so there are two ways we can write it. Okay, you can write all real numbers. So one way I can write it is like this, using a set theorem. So it's from x is between -infinity, because it's all real number. So it's from -infinity less than x less than positive infinity. Okay, another way to write this is you use the symbol set symbol. So x belongs to, like this little e symbol, okay, looks like a C with a dash inside, belongs to the set of all real numbers. Okay, this is a both-face R. Okay, both-face R. That represents a set of real numbers. Let me write it like this. Okay, so x belongs to a set of real numbers. All right. Now, what about range? Now, the range of this function, let's take a look at this. The range refers to the output of the function. The output of the function is the y value. So as you can see, the output oscillates between -1 and 1, right? Okay, this is 1 and -1. As you can see, it goes from 0 to 1, increases from 0 to 1, decreases from 1 to 0, and then decreases from 0 to -1, then increases back to 0. So it oscillates between -1 and 1. So the range will always be between -1 and 1. So the sine function value, the value of a sine function will never be outside the range of 1 and -1. So if you do sine of an angle and then somehow you got 1.26, then you know it's wrong, because it's not possible. The sine function of the basic sine function, that's what that is. The basic sine function value will always be between -1 and 1. Okay, so y is between -1 and 1. Alright, y is between -1 and 1. Alright, now let's look at the zeros. Now, what do I mean by zeros? Zeros means the x-intercepts. Okay, so x-intercept, let's look at the pattern. As you can see, the x-intercepts, the first one is 0, the next one is pi, the next one is 2 pi, the next one is 3 pi. So as you can see, it repeats every pi, start with 0. Okay, so what we're going to do is we're going to write, because there are infinite number of infinite number of x-intercepts for sine functions, so we cannot list them all by writing them all separately. We're going to write them in an equation form. So the zeros is going to be at x equal to, okay, 0 plus minus m pi, okay, plus minus m pi. So n belongs to the set of integers. So we can write n belongs to the set of integers, which means n starts from 0, 1, 2, 3 integers. Okay, I'm sorry, integers. The set of integers is a capitalized, stylized both-face z, which means n start with 0, 1, 2, 3, 4, 5, 6, or n can be -1, -2, -3, 4, 5, 6. But m0 plus minus m pi. So that's, you start with 0 and you plus 1 pi, 2 pi, 3 pi, 4 pi, or you can subtract 1 pi, 2 pi, 3 pi, 6 pi. Okay, so n belongs, and you can do n start with 0, 1, 2, 3, or n belongs to the real set of integers. So, all right, excuse me, the set of integers, not real numbers. I think that was oops, I don't want the blue here. I'm supposed to be in black, right? Alright, here, let me use the black color here. Alright, what about periods? Okay, the period of the function, as I mentioned to go, is 2 pi, because it completes its whole cycle within the space of 2 pi. So period is 2 pi. Alright, what are vertical asymptotes? Okay, now vertical asymptotes are the positions where the function is undefined. Now, as you can see, we have looked at this function. Basically, there's no point where the function is undefined. Okay, now because our domain is all real number, right? So that means we can plug in any numbers and it's not going to give us any undefined or divide by 0 result. So there's none. So let's go ahead and put not available. Okay, not applicable. Now, is this function even or odd? How can we tell? Okay, even function, I'm not sure if you remember from your previous Algebra 2 classes, an even function is symmetrical with respect to the y-axis. Now, as you can see, the sine function is not symmetrical with respect to the y-axis. However, it's symmetrical with respect to the y equal to x. Okay, if you look at the diagonal y equal to x, it is symmetrical with that. You can think about this as flipping twice. If you flip this part of the segment over the y-axis and then flip again over the x-axis, then you will be on top of this part, right? So you take a look at this one, you flip over to the left and then flip down. So if you flip twice and then you will be on top of the graph will be on top of each other, then it is an odd function. It is an odd function. Its reciprocal is an odd function. It is reflexive with respect to the line y equal to x. Okay, and of course the reciprocal here will be, the reciprocal function for sine is cosecant. Okay, it's cosecant. Maybe I should give myself a little more room there. Well, that's good. We'll go ahead and do that. Okay, so the reciprocal function is cosecant. Okay, right. So now let's go ahead and take a look at cosine. So I'm going to turn off sine, but let's just go ahead and look at sine and cosine together. As you can see, the curves are basically have the same form. The curves are very similar. They basically have the same form. The only thing different is that they are offset by 9 degrees by the pi over 2 phase, by the phase of pi over 2. So there's a something called a phase shift. So anyway, let's go ahead and look at cosine directly. Okay, now cosine, look at the domain. Let's start with the domain. Now I'm not proving this to you by showing this, but I'm just showing you that you can see there's no break, and if I keep zooming out, it goes on forever. And because the input of cosine is a real number, so there's always, and it it's a periodic function, so it repeats itself. So we can always plug in any real number, and we will always get any kind. Our output always will be between 1 and -1, so it will always be there. So the domain is definitely from negative infinity to positive infinity. The input from negative infinity all the way to positive infinity. The output will always be between 1 and -1, same as sine. And what's the okay? So let's go ahead and put that down. Let's scroll this up a little bit. All right. So cosine, we also have x is from negative infinity less than x less than infinity. Now we cannot get to infinity, so that's why it's less than. Another way to write this is x belongs to the set of all real numbers. You can plug in anything into this function and get an output. And range of the function is also the same. It's -1 less than or equal to y less than or equal to 1. So it's any number between -1 and 1 inclusive. Okay, -1 less than or equal to y less than or equal to 1. It has different zeros, because you can see the first zero we encounter is at pi over 2. The next one is 3 pi over 2. Okay, so pi over 2 and 3 over 2, they're also 1 pi apart. They're 1 pi unit apart. So basically we start with pi over 2 and then go on as every pi we will encounter a 0, or x-intercept. So the x-intercept will be at pi over 2 plus or minus m pi. Now n can be equal to, belongs to the set of the integers, which is I'm going to use a boldface z. So m belongs to the set of the integers. Okay, let me try to write it out like that. Okay, now you also can say n equal to 0, 1, 2, 3, 4, 5. We also can write it like that. Period is also 2 pi, and there's no vertical asymptotes, as you can see. Now the function of cosine is even. As I mentioned before, how do you determine even and odd? You look at the you look at the y-axis. If the function is symmetrical with respect to the y-axis, that means you can fold the right part. If you imagine you fold this paper, right part onto the left part, and then they fall on top of each other, then they are symmetrical with respect to the y-axis. Then they are even. So is even, and the reciprocal function is secant. Okay. All right. Alright, so let's go down here a little bit. Let me extend the line here. Okay, I'm just trying to make the table look a little better here. Excuse me. Alright, so now let's go ahead and take a look at tangent. Tangent is the reciprocal of cotangent, but tangent is also sine over cosine. Okay, sine over cosine. So it's very important to understand what tangent is. Alright, so let's take a look at tangent graph. Now, tangent is very special because it has asymptotes. So the domain is going to exclude the input where it's not valid. Okay, so the first input that's not valid is pi over 2, and then also everywhere when after pi over 2 you have 3 pi over 2, 5 pi over 2, you can see there's nothing there. Negative pi over 2, negative 3 pi over 2. So that's the place where everything is not included. So definitely what we're saying is x is all real numbers, exclude all the multiples of pi over 2 basically. No, not multiple of pi over 2, I'm sorry. It's only the odd multiples of pi over 2. So it's pi over 2 plus pi, okay? So what we can say is x is all real numbers except not equal to pi over 2 plus m pi, okay, plus minus m pi, and again m belongs to the set of all integers. So when we write like this, we understand, okay, where x belongs to all real numbers except x doesn't equal to pi over 2 plus minus m pi. So those numbers are excluded. Now the range, we did mention last video, the range goes from negative infinity all the way to positive infinity. So range covers everything. So y in this case is from negative infinity less than y less than positive infinity. Okay, or I can write it like this: y belongs to the set of all real numbers. So in tangent, your output can be anything. It can be anything. Now the zeros. Every time you go through 0, you have 0 and pi, so that's definitely is 0. And I'm not sure if you see a pattern here, the relationship between as you can see, the zeros of tangent follows the 0 of sine, and asymptote, okay, we're going to talk about asymptote in a little bit. The asymptote of a tangent will follow the zeros of cosine, which is actually we already see here. The domain excluded the zeros of cosine, so that's where it's going to be the asymptote. So x equal to pi over 2 plus minus m pi. Okay, the reason y excluded the zeros of cosine is because tangent is sine divided by cosine. Sine divided by cosine. Okay, this is a very fundamental fact that we need to know. Tangent is the ratio of sine and cosine. So when cosine is equal to 0, tangent is undefined. Now the period is actually pi. If you look at the picture here, you can see that from negative pi over 2 to pi over 2, that completes one cycle. So that is 1 pi, right? And then starting from pi over 2 to pi over 2, it does it again. It's completes another cycle in a period of pi. And it is odd, okay? It is an odd function, as you can see. It reflects across the y-axis and the x-axis. So if it reflects across both axes, it's odd. So the reciprocal is cotangent x. Okay, cotangent x. Alright, secant x. Let's take a look at secant x. Secant x is a little bit different than what we have seen before. Secant looks like this. Now, as you can see, the domain also excludes some numbers. Okay, let me go ahead and change back to pi over 2 here. Okay, let's go back to pi over 2 so we can see a little bit better. Okay, now you see pi over 2 is the asymptote, right? Pi over 2, negative pi over 2, 3 pi over 2 is the asymptote. Now, why is that the asymptote? Because secant is the reciprocal of cosine. So whenever cosine equal to 0, secant doesn't exist. So secant also has the same domain as tangent. That gives them some kind of relationship that later on we'll explore, okay, and belongs to the set of integers. So secant has the same domain as tangent, and now its range is different though. In range, it can go from negative infinity all the way to negative 1, but then there's nothing between negative 1, and then it goes negative 1 to 1. There's nothing between negative 1 and 1. Then from 1, you can go all the way to positive infinity. Alright, so let's go ahead and write that down. So y means this is from negative infinity all the way to negative 1, and or is from 1 less than y all the way to positive infinity. Okay, so that's okay. Alright, and the zeros, there are none, not available, no zeros. Okay, you have no zeros. Just like sine has no asymptotes, secant has no zeros. It doesn't touch the x-axis. The period will be 2 pi, that's the same as cosine. Asymptotes, the asymptotes are the same as as cosine. Where the zeros of cosine are, so it's the same. The asymptotes is the same as tangent. Okay, and secant is let me take a look. Yeah, it's an even function, as you can see. It's symmetrical with respect to y-axis, so it's even, and its reciprocal function is cosine.